So, let us now start with general foundations. So far we have been capturing in the first part as an introduction and case studies. In the second part we discussed facets of models. In the third part we covered model development and model utilization. And now we are going to general foundations. This is our list of topics we covered already. Only to remember, now in lecture 17 we are going for the history of models, for the foundations of models, and for this reason we would like to discuss paradigms and principles of modeling, somehow revisiting the notion of a cargo, the logos and Platon's analogies. Furthermore, we would like to show that we should extend our current treatment of models and modeling towards a science of modeling or a culture of modeling, and finally we should come down with modeling to model and models as a discipline. A model is a systematic, well-developed description of some situation with mental language means. It often uses science, and especially in computer science and in computer engineering, we use a number of languages. It describes a situation, and of course the modeling science should be based on a theory. In general, we can consider that we have already 5,000 years or more of modeling experience, starting with modeling in Egypt, in Greece, in later Babylonian time, or looking for the work of Thalheim and also for the work of Bernhard. Let's go for the classics. There are 3 analogies, and one of the most important analogy is the analogy of divided line, introduced by Platon. Platon has been somehow distinguishing as a line. In this case we revisit a little bit to have a planar representation. First of all, visible and physical things, then we can have science, then we have concepts, and then we have theories. The first part is the visible world, the second part is the intelligible world. And in this case we have at least somehow a differentiation between the visible and intelligible area. It is based on conceptual contrast, based on some kind of observations, and of course in this case we do not really consider the reality, but we consider only the observed reality, and we can imagine a virtual reality. Klaus Lattmann has been reconsidering it, and I would like to go further with an explanation of these analogies. In general, there is a tetralogy: the analogy of divided line, the analogy of sun, the analogy of the cave. The analogy of the cave says we see only what is visible for us, or made visible for us at the cave wall. The analogy of sun states we see only what is visible and not what is not visible. And the divided line is somehow displaying our mental world, our intelligible world against the visible world. Old Socratian philosophers have been considering the nous, the logos, the arche. We might also add the techne, and this is the separation that has been already introduced by Heraclitus. Platon extended it, Aristoteles, the first from which something is, becomes, or is recognized. So in this case we have the arche. The logos is somehow, in our understanding, the model. The nous is the general capacity, world, spirit, mind, simplicity. And additionally, nowadays we have to consider also the artificial world. as design, development, utilization, production, creation, output. That means the techne. We would like to revise this approach a little bit and come to a novel approach. The analogy of divided line is better displayed, as I showed already, in a two-dimensional form. And we want to separate the visible world, the mental world, and the intelligible world. And of course, in this case, we have a good number of problems we should somehow resolve. I have here a German explanation of the logos, nous, arche as a triptychon of model, basis and foundation. I think it's better even to state in German. For this reason I left this slide in the German language as well. The logos is not only the word, as in Goethe's Faust it was written, in the beginning was a word, citing Martin Luther's Bible translation. The logos means more. It means, of course, the meaning, it means the handling, it means also the reasoning. So in this case, we can now consider at least 4 different worlds of a human. The observation world, whatever we can observe, maybe also whatever we can observe and reference by terms. The mental world, that is our compilation, based on perception models that somehow represent the origins we observe. The intelligible world is some kind of formation of a world of theories based on conceptions. We use perception model of a community as origins, and we derive conceptual models of the intelligible world. Furthermore, we should also consider the techne. That means our application world. We have the vocabulary and the understanding of our technical application world. It could be also based on ontologies or anything else. There is an agreement in a community living in some application world, and in this case we use some kind of domain situation models as one of the forms of settled mental models as origins. And again, we derive conceptual models of the application world. So, in this case, we revise now the 3 analogies of Platon. First of all, we should say, okay, fine, we have some kind of quantitative and some kind of qualitative parts. The qualitative part is based on our cognition, our insights, our findings, our knowledge. And for this reason, we could call these 3 parts, the first 3 parts and the knowledge, kingdoms. There's the observation kingdom, that means observable physical things, praxis. That is reflected by shadows, reflections, phenomena, going back to the analogy of the cave. Somehow compiled into our mental world, based on our model beliefs, intuitions, probable predictions, based on our perception models. We can make our conjectures and explorations and explore existing and domain situation models. And then we might go for the intelligible world. So this is a thought kingdom. It is based on formation, on ideas, on amalgams, on conceptions and concepts, on signs of things, and might be represented by conceptual models. The intelligible world in the compilation consists also of theoretical models, forms. So this is the real noesis. That means in this case we can now go and look for our 4th part. We have been introducing the application world or the technical world. The technical world represents the 3 different parts, the visible world, the mental world and the intelligible world, by technical things, in the meaning of the technikos, activities of design, development or exploitation, and also formal procedures, the sum of means and rules for producing products. This we have been already considering with the part about development of models. The technical course is often based on handicrafts or trade. It is becoming an art if we have the ability to carry out a certain activity properly and oriented on the quality we have in mind we require. The reasoning world is then again based on the three analogies. We have very different kinds of reasoning. We'll come back in the reasoning part of this lecture again to this separation of concern. We have a classical causal mechanistic reasoning that is based on the law of sufficient cause. We have also some kind of probabilistic approach to reasoning. And in this case we ask not only for the why, we ask also how and what and the rest of the W*H framework. That means in this case our reasoning world reflects in this case the outer possibility, our inner possibility, and our intelligible possibility. And in this case we come back again to finally to a theory-backed reasoning. That means in this case, if we go again for reflection, we have at least two different directions. We have the quantitative direction of the observation kingdom especially, and we have the quality direction especially of the thought kingdom. In this case we can say, okay, fine, we have things that are not observable, we have origins or originals observable as shadows, and we have original systems observable as shadows. We might have no glimpse what happens there and somehow have to observe what happens. In this case we have impression models or phenomena models. We might also perceive, believe, somehow conjecture and come down to mental modelings, and then we have in the case of systems domain situation models. In the case that we observe the origins on their own, then we have perception models. And if something is not visible, then still we might have suggestion or experimental or hypothetical models if we even compile those. And finally we come as a last to the rationality, formation, reasoning, reconsidering, ideas reconsidering. In this case we have conceptual models for origins and conception-based models for origins that are systems, again observable as shadows. Okay, this leads us now directly to principles and paradigms. Modeling has its own basis and background that is pretty similar to the instrument. Let's talk about some of the principles. There is a conceptualization principle. Only conceptual aspects of the application domain should be taken into account when constructing a conceptual schema. There is also a 95% principle, often called 100% principle, namely all the relevant aspects of the application domain should be described in a conceptual schema. There is also a formalization principle. All concepts and of course the model itself should be formalizable in order to be somehow computable, compilable, implementable. There is a semiotic principle. We would like to have somehow a way to express our thoughts, so the schema, the model, should be easily to interpret and to understand. There is also a correspondence condition for knowledge representation. The models should be in such a way that the recognizable constituents of it have a one-to-one correspondence to the relevant constituents of the model. We have furthermore an invariance principle. Conceptual schemata and models in general should be constructed on the basis of such entities found in the application domain. Found means in this case observed in the application domain, that are invariant during certain time periods within the application area. And there is a sub-model principle or sub-schema principle. In order to construct a good conceptual model or a good conceptual schema, it is important first to construct relevant sub-schemata and then to search for connections between them. These are principles that have been developed mainly based on some kind of Persian organization of our modeling techniques. I refer here to Esco Mariamar. There are some very general, well-known principles, but the problematic part is that the theory is not really completely available. First of all, we look for a principle of separation of concern, and tight separation into components leads to modularization. We base our reconsideration on components or somehow parts. We try to orthogonalize, we try to parameterize, we try to have some kind of, let's say, information hiding principles like the Parnas principle of information hiding or the Liskov substitutability principles. So in this case we can say, okay, fine, our components have interfaces, represent views, have some kind of hierarchies, have some obligations, some responsibilities, they can be integrated, they are dependent from each other or independent, they might be incomplete or fuzziness. In this case, we look for components that can be easily extended, and in this case we look for an open world representation. And of course in this case we need to have some kind of data functional control decomposition. There are several techniques for modularization, like the skeleton technique, that we are considered first the skeleton and then the flesh to the skeleton, or some crystallization techniques, so that we can have a component that is somehow closed and can be somehow replaced if by something else that has the same components for the outside connections. Another very difficult principle is the abstraction principle. We have already been considering the 4 different sides of abstraction. We have, in this case as a general principle, some kind of component or construction abstraction, some context abstraction, some implementation abstraction based on pattern techniques and refinements. Another principle is coupling. Coupling can be done in a lazy enforcement mode, or it can be done in an easy enforcement mode. It could be tight or loose coupling. We might consider only integration, or we might consider collaboration as a principle how to build a model as well. This leads us directly to principles that are used in design science. We might have the principle of multiple interpretation. Anything can be represented in very different ways. We have a principle of suspicion. Are different problem perceptions and definitions guided by biases or systematic distortions in the narratives of the participants? That means in this case we should ask us whether the model representation is a real proper one for our community of practice. We have a principle of interaction between the researchers and the subjects. That means we should have some kind of interaction, and we should have some kind of very nicely settled meta model for interaction. We have a principle of contextualization. Some context can be omitted, another context must be somehow put to our deep models. We have the principle of dialogical reasoning. That means reasoning should be made aloud. That means in this case we should have some kind of possible language use for expressing what we want to have. We can boil down these principles now to design principles. We have data design principles in database development or database modeling. We have database portfolio explication. In this case, we have a number of different approaches to database portfolio explication and to data design principles. The list here is not full. The list is continued by constraint management, by general design principles, keep it simple and stupid, is one of the pretty nice general design principles. You see here a good number of sub-principles you can observe in database design. You might have also problems with some kind of design principles. Some people claim that a relational database schema is not a conceptual model. We claim, however, that it is a conceptual model. Some principles are somehow controversial, some of them are even spurious. So in this case we should somehow avoid them whenever it is possible. There are already known a number of poor database design mistakes, the classical relational mistakes, the classical ER mistakes, the classical XML mistakes, whatever language you use. Modern mistakes are, of course, hypes for getting the past experience. Anything must be now better. Experience is based on modeling in the small and never on modeling in the large. Neglecting the heritage we have been already obtaining with our research approaches. Back to sequential programming instead of multiset or set or collection oriented modeling and programming. Modern representation features are not integrated. And one of the bad mistakes that is really somehow not understandable is that a model is only used as an inspiration model for later programming and for later installation. For multi-layered modeling, we have been using model suites, and in this case we introduced already in the model suites chapter a number of principles: downward dependency principle, upward notification principle, neighbor communication principle, explicit association principle, cycle and elimination principle, and layer naming principle. I refer to the model suites chapter 9 for an explanation of these principles. We should have also maybe to consider some properties or some meta paradigms of modeling. One is monotonicity. That means any kind of refinement should not lead to complete revision of the entire model. A model should be built somehow in an incremental way. So in this case we can be sure that the inner parts are behaving well as the added parts. We have of course also a finiteness principle or finiteness paradigm. Any quality criteria can be checked in finite time, applying a finite number of checks. Application domain consistency means in this case we develop a model that corresponds to the requirements and obligations of the application domain. We have also some kind of conservativeness. Any model revision that cannot be reflected already in the current specification is entirely based on changes in the requirements. Then we achieve that model development is somehow conservative, easy to maintain, at least for the consistency and coherence of models. We have, of course, the neatness, so in this case we can also consider the economy of modeling. This allows us to reason also on properties. What is the subject of modeling? What kind of quality of the model we want to achieve? And what is the economy of modeling? Economy means, in this case, we should have, of course, some termination conditions that allows us to say that this model is now a proper one, it fits to the function, it serves well, and for this reason we can consider the model as partially finished. Okay, it is often claimed now that modeling is mainly only apprenticeship, sometimes art. It should, however, become science and culture. In general, it is nothing else as a level of majority of the instrument being of models. Apprenticeship is not the proper thing. We cannot rely on something that has been made in this case. The art follows the interpretation of the art of programming published by Donald Knuth. That is the way how we do things. Science is a bit more. Apprenticeship is a bit better than any kind of manual skill or somehow corresponding to handicraft. But anyway, we need, in this case, to have some kind of formation of our modeling skills. In my understanding, this kind of organization of modeler education goes back to the code of Hammurabi of Babylon. So we have to teach the craft to the next generation. If we distinguish now art, science, culture, then in this case we might have this kind of ladder. First of all, we have some kind of communication ability or some collaboration ability. That is nothing else as some kind of life intelligence. Next, we have a problem-solving intelligence. Then, the intelligence might allow us to have a self-reflection that goes towards science. If we continue further, we have maybe some kind of design intelligence and real-life intelligence. And finally, maybe we should consider also wisdom. With collaboration intelligence, we are laying the foundation, we are conditioning and socializing. With problem-solving intelligence, we have some kind of enabling facility that makes a solution of a problem possible. In science, with self-reflective intelligence, we of course know what we are doing and we have a foundation. If modeling becomes really a common culture, then in this case we can talk about design and life intelligence. Okay, so in this case we can now distinguish between the art, as maybe the current handicraft and skills in planning, making, executing, as capacity to do things well with a large, let's say, research agenda still. We can also head towards science as constructive theory, maybe also other theories, but I would expect it as at least a constructive theory that is based on principles, on the technology of modeling, on reasoning abilities, on theories in whatever sense, on, let's see, on norms. It allows us to handle modeling as a discipline and has, of course, a systematic theory. Culture means, in this case, it is practiced and well accepted, theory-backed technology and engineering. Culture can be defined as a collective programming of the mind. If you consider the current situation, then in this case we can observe that we are mainly talking nowadays about the art of modeling. Very seldom about the science of modeling, and I do not know any reference about the culture of modeling. Okay, let's a little bit more in detail consider the ladder of intelligence. The background says nothing else. We are able to communicate, we know a language, we can explain, we can recognize, we can also state that we completely accept the grounding and the background, and we are introduced to the basis and we are common with it. So in this case we have at least the ability to handle it. The background, to remember, was based on a grounding and the basis. The grounding is undisputable, the basis can be changed, and in this case we have some kind of, let's say, normal, maybe we could also call it life intelligence. The art of modeling can be directly based on how Donald Knuth was introducing the art of programming. Art means in this case a skill acquired by experience, study, observation. It could be a branch of learning. It could be an occupation required, maybe requiring also skills and knowledge, as maybe the main interpretations of the art of modeling we would like to have here. In this case, we use this art as a basis for problem-solving intelligence. We execute, manage, establish. Of course, we are inspired and guided. We imitate, guide, instruct, know, use, analyze, are able to apply, to manipulate and to check. Art is in this case a creative skill and, of course, also combined with imagination. We can have different levels of artisans, as we did it already with the CMMI or the SPICE approaches: defined, performed and controllable, managed, properly controlled, predictable and optimized as maturity levels in the art of modeling. In this case, we go with a problem space and we search for a solution space. In this case, we can say, okay, fine, we specify the space, we specify the actions to transfer state to state. We have maybe also goal testing, and maybe we have also a problem solution controller. And this is in general based, as I already have been introducing in chapter 11, on Polya's problem solving frame for mathematicians. You have the problems, the context, the forces, and finally the solution. We can go in the same way for a foundation of modeling. Let's go now towards science. Science is, of course, a system of knowledge. It's based on what we want to somehow express, explain, investigate. We have a number of different properties of science. And in general, science is somehow allowing us to comprehend, to establish, maybe also to create some kind of theory. It is based on understanding, describing, explaining, specifying, predicting, interacting, applying somehow, of course, conceptualizing, idealizing, formalizing, practicing, and so on. A science in this case is, in our understanding, a modeling science, a system of modeling knowledge. That entails, of course, unbiased observations and systematic experimentation. It is systematized. It uses scientific methods and laws. The basis of a science is a theory. That is now a bit problematic because we have a number of theory notions. A theory could be simply a belief, a policy, or a procedure proposed or followed as a basis of action. A theory could be something that is taken for granted, especially on trivial or inadequate grounds. So in this case we need maybe a proper explanation what is a theory. We use three different kinds of explanations for this theory. Most people consider only scientific theories as theories. A scientific theory is a structure suggested by laws of representation, laws of observation, and is devised to explain them in a scientifically rational manner. A theory could, however, also be an offer. It is maybe an explicit and systematic discussion of foundations and methods. We have a number of disciplinary theories that follows this kind of theory understanding. A typical are disciplinary theories, and especially constructive theories, how we use, for instance, in our database business. The best explanation for this goes back to the explanation that Vitruvius, Alberti, and Gottfried Semper made as, let's say, a collection of settled instruction conceptions for development within practical, maybe, situations. It is an underpinning of engineering. It has various facets. A theory could be also nothing else as the opposite of practice. That means in a practice-oriented apprenticeship, a theory is nothing else as the counterpart of acting, of the practice, of a systematic generalization of experience, of systems of main ideas. Which theory we are using for our modeling theory depends on the application area. We have a number of other explanations of theories. I took here some of those that are published in the dictionary.com. I took another one from WordNet, another one from Collins English Dictionary. You can have also more versions of a theory. I think it is better to use a theory, as we do in most computer science and computer engineering approaches, as an offer. We would like to have a scientific theory, but I think it is a little bit too far. That means in this case we have some kind of reflection, of self-reflection of what we are doing in modeling and how we are handling it. I would like to go back to an old work by Parsons and Schills towards a general theory of action that has been also somehow systematized by McNeil. And in general we can say, okay, fine, a theory as an offer is nothing else as filling the W star H questions, and in this case we can specify what kind of theory we would like to have. Which one is necessary for which kind of modeling area depends a bit on our acceptance in the community of practice. We have a number of elements of such a theory. We should have a clarification what is a model. We considered it already in part number 6. In which cases the model is adequate. In this case we need a number of criteria. Again, chapter 6 explained it. What is a good model? Again, back to chapter 6. How models can be integrated and composed. See the chapter about model development. What are correct activities for modeling? We considered also in chapter 11. What is the added value of a model? That goes back to the model quality. Who can use the model? How? In which way? What are the background theories of modeling? We will consider in the next chapter. Why should this model be used here? Where? In what way? And by what means? We considered in the deployment and utilization chapter. That goes back to the knowledge that is directly inside the model. I left here my German slide because if I didn't find the correct translation back to English for Thomas Kuhn. Thomas Kuhn inherited mainly what Ludwig Fleck has been developing. And in this case we talk about a disciplinary matrix and use symbolic generalizations. We use reference models and some kind of prototypical generic examples. Knowledge is backing models and modeling theory. There is not at all an agreement what is really knowledge. I like the notion of knowledge is sustainable, evolving, potentially durable and verifiable, grounded consensus. So then in this case we can distinguish knowledge as a state of information of a user and the general knowledge. This notion with these 8 properties is, in my understanding, a proper one for understanding what is a knowledge that is backing our modeling and our models. Okay, let's go to the next. Design intelligence. That is, in real life, we are organizing, we are designing, we are modernizing, and the design is really proper. Culture means in this case, according to Hofstede, is a collective phenomenon which is shared within the community of practice. It consists of unwritten rules of modeling, of the modeling game maybe. It is the collective programming of the community of practice. It consists of principles, methods, guidelines and practices. And in this case, design intelligence is now to make a thing in such a way that everybody can accept it in a proper way. Okay, we have already tried to develop a culture, at least for software engineering. See for instance the TOGAF, the open group, how it is explained what we should do during development of proper software that is acceptable by the real users. Okay, the last step is now wisdom. I think it is a less explainable part. It is of course consisting of accumulated learning. It is an ability to discern inequalities and relationships. It has some good sense. It is generally accepted belief, wise attitude and course of action. In this case, of course, we have some kind of, let's say, school of modeling. To reach the wisdom dimension, I would somehow schedule for the next century. So now we can go and dream about modeling as a discipline. We have already noted that models are used everywhere by everybody in all sciences, in all engineering and technology disciplines, and also in daily life. So it means in this case we might think that modeling should be really given as a proper sub-discipline of any discipline. I would like to go back to the discussion we have had in the conference Modellierung 2019. What would be the typical content of such a modeling subdiscipline? First of all, since we are considering mainly model suites, we should know how co-model development is done in a proper way. And this will directly lead to some kind of education by separation of concern and model suites development. We could use also modern software engineering approaches. We understand and apply modeling languages for different perspectives. We have a really appropriate selection of models. We associate these models. We check whether the model candidates meet our given requirements, and we evaluate concrete model instances. There is also some kind of background that can be taken from database research. Understand and use a structural modeling language, understand database systems quality criteria, transform models into a database schema, transform application models into database models, database quality oriented optimization, sometimes called maybe normalization or advanced normalization, understand and use modeling languages for different perspectives. So it means in this case you could directly inherit what has been done in this research category. Furthermore, of course, we need a proper handling of logics. As already discussed in chapter 4 about languages, it should not be only the first order predicate logics or the propositional logic, it should be more. We could use also what has been done in object-oriented programming, understanding of principles, some kind of dichotomy, some kind of inheritance, encapsulation, composition, substitution, and substitutability. And if we go further, we should have also some kind of theory. That means in this case we could use what we gained so far in theoretical computer science as a background for actions in modeling. And then we can say, okay, fine, if we would have a separate module for modeling, we should maybe have some kind of explanation what are model suites or multi-models, what is concurrency, structure, abstraction, and logical thinking. Next, we could try to develop an understanding what is content, what do we want, what is mediation, which kind of approaches we have, think about a little bit about didactics, perspectives, abstractions, and maybe modeling and returning. And furthermore, we should go for languages and frameworks so that we can use our modeling subdiscipline in a proper way. It requires, of course, in this case, didactics. It requires also how we do it in computer science in a naive, realistic way. In this case, we would have also to consider that models are never, or pretty seldom, greenfield models. That means they are developed from scratch. So in this case, we should handle brownfield modeling. That means in this case, we should know how to handle legacy, what is heritage, how to partially redevelop stuff. If you think about modeling education, we should also think about some general topics, dealing with the tools of trade as a cultural achievement, mathematical methods, which are the basic structures, how we can formulate a problem. We might go for Bloom's taxonomies. What is the credit of our solution? Be aware of bad solutions done by bad softwares. We might have also some kind of taxonomies, like the one by Anderson-Krathwohl, understand, next apply and transfer, next analyze and evaluate, next generate. And of course, we should also have at least an understanding of the use of models in a proper way, so that we have really a good return of investment. If we go for conceptual modeling as a discipline, I could use the thesis John Melopoulos has been recently presenting in an ACOS talk. Conceptual models are often models of mental representation. In this case, conceptual models use a codification of mental concepts. Whether conceptual models should be computational is a little bit, let's say, questionable. Whether they are conceptualizations of the world by some community of practice, we can also have a longer discussion. It is undisputable, however, that notions are atoms of conceptual representations, of mental conceptual representations. Concepts might have a propositional structure, not only an associationist one. We would like to have a coherent set of concepts. The second thesis is conceptual models are artifacts. So it means in this case we can have some kind of quality and quality tolerance of our models, and we can say, okay, fine, what is the function of a model, how the function is fulfilled, and what we would like to have. Another conjecture by John Melopoulos was conceptual models are social artifacts, because of we are socializing in our community of practice, and of course we have to share our conceptualization in order to understand each other. It could be based potentially on argumentation theory, I would claim. So in this case we have a schedule for a theory of models. Models in general: purpose, goal, function, adequacy and dependability, background, functioning and effectivity, quality and evaluation of models, and somehow providing also a cargo, or at least an informative model of the models we have been developing. One thing that could help us is model profiling. Model profiling says what kind of model we have, what are the specific properties of the model, how we handle the problem. This is nothing else as what to do with data profiling in database research. For this reason we might use it by schema definition, by business objects, by domains, by data sources, by table definitions with a large number of specific parts of that. We might use synonyms and namespaces, data rules, value results and issues. We could also consider the discipline of modeling by combining conceptual modeling techniques and design science. What we would like to have in our most mediation-oriented modeling approaches, we would like to have a transfer from the state of affairs to an extended, maybe also distorted state of affairs. In this case we have some reality, and we would like to construct an extended, maybe a distorted, idealized reality. Then we start with somehow observing what we have, with designing what we have, with understanding what we have. We could directly go from, let's say, describing or prescribing to creating and construction, or maybe to deploying, and then to establish by creating and construction the new system. We could also go a step upwards and can say, okay, fine, let's look for the rigor cycle. The rigor cycle is to compile our experience we got and then to integrate it in a matter how we envision for a modeling culture, and then we can even predict what we get as a system, and again we can construct a system. One thing is modeling economy. We should not model forever. We should stop at a certain step. And we should use some kind of Solomonov or Occam's razor principle. We are not looking for the best possible model, but for some minimal and sufficiently good model. The model should be also revisable, evolvable, integratable, and modernizable. Models are typically model suites, so in this case we should at least know what coherence means or what kind of association schemata we could use. Models are representative collections of origins, but not all origins, but only of some of them. Model development is work and thus must have an appropriate stop or termination criterion. That is a very important part of modeling economy. We should know the limitations for sources, inherit what has been can be inherited, and spend as much as necessary, but not more. Okay, let's talk about the future of our modeling discipline. First of all, there are some megatrends. Megatrends are quite often somehow regulated by hypes. There are some challenges. There are some next steps, and again I took this list from the discussion, or my compilation of the discussion in Modellierung 2019. We should also talk about the why, about the deficits today. We should overcome the Babylonian confusion. Wolfgang Hesse said, in this case, our language confusion is already reaching the level of the dinosaurs. We should also incorporate a modeling theory into the tools so that we can use really whatever has been done in the past. The secret of the success of database management systems is based on the low principles. Let others do the work and then use the work. The modeling culture is something what should happen in the future. Yeah, and then we can also improve the practice of modeling. Make models as a part of results, integrate modeling in system development, reduce effort for modeling, maybe using proper tools and somehow reusing reference models or generic models in a proper way. Provide customized models for domains, how we do quite often for domain specific languages already. Linking models from different views and perspectives, from different participants. Examine the benefits or the benefit factors at least of models. And of course we should somehow extract, like in the rigor cycle, the knowledge and the skills of modeling. Okay, in the last part I will come down now to model-based reasoning. A lot of these methods we have been already considering in the previous chapters. Here we talk about life intelligence, collaboration intelligence, art of modeling, science of modeling, maybe also culture of modeling, with many methods. I would like to remember the fundamental tenets of modeling science. We have been already considering for conceptual structures. I would like to remind the reasoning frames. We can go with positivism and rationalism, One is based on induction and deduction. The other one is based on abduction and verification. We have a good number of very good thoughts about it, so we could reuse it. We could also use model-based reasoning, as we did in databases already, quite properly for database modeling. We could also go for model-backed reasoning, as I was putting here as an example for Egyptology. We could also go for hypothetical and investigative modeling, depending on what we have here in mind. We could also use exploratory and consolidative modeling. I introduced already these parts when we have been developing our methods to develop a model. Please remember also the pitfalls and opportunities of explorative modeling. Some typical problems to model are evaluate benefits of proposed policies against costs, forecast value of variable of time. In this case we have a number of methods we could use, from decision making. To remember, I should also models for statistical computing and decision making, for causal reasoning and modeling, for network reasoning, for evidence-based proxy modeling and reasoning, and finally also for meta reasoning. So this is a step in my understanding towards the wisdom of modeling. It will become the basis of a modeling theory, reasoning about the reasoning cycles, development of controllers and tracers. The goal is to improve the quality of decisions by spending some effort to decide what and how much reasoning to do about modeling, as opposed to what modeling activities to do. It can be also using introspective monitoring. It is, of course, especially for model suites, based on team modeling. Meta reasoning is, of course, also reasoning about a deep model. Meta reasoning is also about moles in the matrix. And one of the principles could be based on Simon's The Art of the Artificial, the principle of bounded rationality, so that we could accept what has been done. Human reasoning goes far beyond machine intelligence. I would like to illustrate it in very simple examples. You have here 3 pictures of mine. Now we can use some kind of software to extract how this young guy would look like in an age of 65. Or how this young guy would look like in an age of 70. They look a little bit different. You could also use machine intelligence to compute how this guy was looking when he was 15 years old, and how he will look like when he's 17 years old, 70 years old. What is the right one? This one, that one, or that one for 70? I don't know. But in this case, our human reasoning goes far beyond. You see the similarity, and you see that these are 3 different computed pictures. They have nothing to do with reality, and this one has nothing to do with that one. Okay, finally, what we would like to lay down here in this chapter was the foundation of models, of modeling activities, and of modeling. We have covered so far that we are surrounded by models. We use models in a very wide spectrum of application cases. We can base our foundations on Greek philosophy, especially Socratic philosophy, but also in ancient Egypt already. People have been made a sophisticated use of models, so at least our discipline is at a minimum 5,000 years old. What we should also do is to consider, if we go for culture, design concerns. Design means in this case to develop in a proper way the model we would like to have. There are a number of topics we could use. Typical were use of design principles, notions and conceptualization behind, especially in the background. What is my fault? What of others? What kind of feedback? What kind of constraints? What proper design by making appropriate actions perceptible and somehow maybe inappropriate ones invisible? We could use the power of observation and visual inspection. I would call this as the Winnetou detective or pathfinder skills that should be combined with model development and utilization. And we should also establish the principles of visual cognition and communication I was already introducing in the language chapter. Design is nothing else as humanizing our instruments so that we can use the instrument directly in a proper form. Think of the case that you rent a car. You would of course expect that the car has some generic model behind that says where are the brakes, how to use ruling, how to switch on the machine, and in this case you know how to handle it. Of course you can overdo it, like we do for instance in the mobile phone business. I expect that soon the mobile phone will also be used as a pencil sharpener. Of course we follow some kind of principles, especially principle of psychology of modeling actions. And we have a paradigm. Form follows function, that we explained already in this case. Okay, I think I explained why we need foundations, what kind of foundations we have so far. I claimed that humans reason in models. We are surrounded by models. Models must not be precise as possible. They must only be useful as possible. We use a number of approaches. The added value and the economics of models and modeling should be considered, and of course we should consider also evolution and changes. Okay, in the next chapter I will now try to give a number of modeling techniques and of foundations for the methods. We can in this case go back to logics and mathematics and use first a number of logical calculi as a main basis for reasoning. Mathematical foundations and method foundations are still to be developed, and I will show only some of them here. Okay, thank you. That is now the part about chapters for, let's say, foundations of models. Next we go for the difficult part, for mathematics.